Okay, so let's summarize where we're at currently. What we've seen in the previous section is what we call the inference phase of the optimization. We've identified some trainable parameters and the desired output we want to achieve. We have some function that turns those parameters into an output, and we have a way of measuring the error between the current output and the desired output. Now, making this more concrete for our problem, the trainable inputs in our case are the bitmaps, and the desired output is a downsampled rendering of the reference material. We turn our bitmaps into an output by rendering an image of the material, and we can compare the current and desired rendering by computing the loss between the two. The last step we have to figure out is how to close this loop and figure out how we need to adjust the inputs to make the error smaller. That completes the optimization. This is something called the backwards phase, because we need to run backwards through our code to work out how the inputs need to change to make the loss output go down. But how do we actually do this? We can figure out the answer by looking at this problem from a math perspective, although I promise that I'll keep the math to a minimum for now. What we have is a function that takes some input x and returns an output y. And in our case, the input is the current parameters, the function is the loss, and the output is the current loss value. And the question that we're asking is how x needs to change if we want y to go down. And the answer to this lies in the derivative of the function, which relates a change in the input to how the output changes. Now, you've probably already spotted that the slide calls this the backwards derivative, as opposed to the forward derivative. We'll go into much more detail about what that means in a later section. But for now, you should know that these are the same thing as far as the math is concerned, and the difference only starts to matter when you put this into practice and you write programs where you compose many functions together and want to take the derivative with respect to many variables. But in any case, once you have this derivative, if you want to change the loss by some small delta, then we just need to change the input by delta times the derivative. So that's simple enough. That's the math side of things. But how do you translate this into practice? Well, we know what our inference function is, what f is in our case. It's just rendering the mapped material and then evaluating the loss compared to the reference, right? But how do you get the backwards derivative of this function? Well, in most languages, you will have to pull up the Wikipedia page on differentiation rules and go through your entire code line by line and manually write the backwards derivative of each one. This isn't necessarily difficult, but it's very tedious and time-consuming, and it's easy to accidentally make a mistake and ruin your optimization. The worst part of this is, though, that if you change your inference code at all, like changing out the material or how you render or even just tweaking a single line of code, you need to go and change your backwards derivative to match. So this is work that you would need to do over and over as your code evolves. What would be much nicer is if you had some way of magically just generating the backwards derivative of your code to take this work off your plate. Well, Slang was built to do exactly that. We can just say that we intend to call the backwards derivative of a function, and the Slang compiler will generate and optimize the backwards derivative of the entire code for us at compile time. Not only is that much faster and more convenient, but it always keeps the backwards derivative in sync when we change our inference code. So what does that look like? Well, now that we have this capability, we can write a new function to calculate the derivatives for our optimization loop. We pass it the current bitmaps and reference material, and then we evaluate the color of the reference, which is just downsampling, and then we compute the backwards derivatives of the loss to figure out how our bitmaps need to change to minimize the loss compared to the reference material. You might notice that besides the current and reference material, we're passing some other parameters that we're not optimizing. These determine sort of for which pixel and for which light and view direction that we're optimizing the loss. Now, in our case, we want the whole texture to look good under any light and viewing condition. So let's pick random directions so we have even coverage and run this function for every texel in our material. Of course, you have total freedom to change this, depending on what your application needs. For example, if you know only parts of the texture will be visible, you can choose to only optimize those pixels. You don't need to cover the whole space. Or you can re-weight it. If you know, for example, you'll mostly look at the material from the front, then you can change the distribution of directions so you optimize for the more important directions more often. We still need to resolve one mystery, though. When we call backwards diff, where do those derivatives actually go? They don't come out of this function at the bottom. There's no return value with the gradients. Well, there's no magic here. In fact, what would happen if you called backwards diff right now is that the compiler would complain to us, saying that it found an operation in our inference code that it doesn't know how to differentiate. In our case, this would be where we read the parameters from the input textures. And this kind of makes sense. Most of the code in our program consists of mathematical functions and arithmetic, and for these, math defines a clear derivative, and Slang can generate it for us. But reading from memory doesn't have an obvious derivative, and the Slang compiler is asking us for what we want to happen here. One of the powerful things that Slang lets us do is define our own derivative for any function that we want. In this case, well, getAlbedo takes a pixel and returns an albedo value, and Slang will want to call the backwards version of it with the derivative of the return value of that pixel. Now we'll cover this whole autodiff mechanism in much more detail in a later section, but for now this is actually all that we need. We can just take that derivative and store it in a separate texture of albedo derivatives. And then of course we do the same for the roughness and the normals. So that's most of the backwards phase complete. The last missing step is how to adjust the current bitmaps given that we know what the derivatives are. And now if you remember from this earlier slide, if we want to change the output by some delta, then we need to change the input by delta times the derivative. Now pattern matching this to our code, the inputs, well, that's just the current bitmaps. The derivatives, that's what we just computed in the backwards phase. And this delta is actually a free parameter that you can choose. And this is commonly called the learning rate. Now you might think, well, we want the loss to go down by a lot. So let's choose a really large learning rate. But what I haven't mentioned is that this formula at the top of the slide is only true for small deltas. And how small they have to be depends on how complex your function is. And you might have to experiment a bit to find out the ideal value for it. For now, let's choose some small value like 0.01. And if our optimization works well, then we can try increasing the delta to take larger steps and make it optimize faster. Or on the other hand, if it fails to optimize or it blows up, then we can try again with a smaller delta. Putting all of this together now in our Python main loop, we'll add a new call to Slang to calculate the gradients of our loss, passing in the current bitmaps and a newly allocated texture to receive the derivatives. And then we do one step of the optimizer with the calculated derivatives and the learning rate that we chose. That's sort of one iteration of the backwards phase, and now we just repeat this many times until we converge to something. So let's go ahead and try this. So on the left here, I'm showing the results that we would like to get. This is the reference, which is just downsampling a rendering of the original material. And when we render our bitmapped material, well, it should look like that, hopefully. But in the middle is what we get sort of with our initial attempt of just downsampling the textures and hoping that the rendering matches. This looks much shinier than the original, and it has these sort of weird little sparkles. And you can also see this when you compute the loss for this texture. And now let's see what happens when we run our optimization loop to get the bitmaps instead. That sort of try to minimize this loss. Well, this doesn't look like what we want at all. So what's happening here? Why is this not reducing the loss? Why does it look so weird? Well, there's a complication here that has to do with our optimizer. So if you recall, we used the formula at the top of the slide to take an optimization step, and that depends on the derivative of the function that we want to optimize. And there's actually a small problem with how we compute those derivatives. I briefly touched on this earlier, but, well, we want the texture to look good from every angle, right? Every view in light direction. And actually, the correct thing to do would be to evaluate the loss for all possible light and view directions, sort of exhaustively iterate over all combination of directions and sum up the loss for all of them, and then take the derivative of that. But that's really expensive, right? That's like rendering an image of your material times, the infinite number of combinations for light and view direction. And what I actually ended up doing is just randomly picking a single pair of light and view directions and then compute the loss just for that single pair. Now, it does give you the correct result on average, if you sort of average the loss for many combinations of these. So it's not completely wrong, but the main consequence of doing this is that our gradients are now noisy. And the optimizer that we chose just can't cope with that. What I described so far is something called gradient descent, and it's just about the simplest possible optimizer you could use. But there are much better ones that can deal with noisy gradients. They're not hugely complicated. Most of them work on the same basic principle, which is to just use sort of a moving average of your gradients to smooth out the noise. But something even better is what's called the atom optimizer, which has been so successful that this is what everyone uses by default nowadays. Now it does this moving average that I explained earlier, and it contains some extra smarts to rescale the gradients to have the right magnitude. But I'll direct you to the original paper and the many web sources explaining it if you're really interested to learn more. For our purposes, it's a small piece of code that we can use as a drop-in replacement for our gradient descent, and we can go back to actually doing the optimization. So now let's rerun this optimization, but this time with an optimizer that can actually handle noisy gradients. And yeah, this looks a lot better. We actually get a good-looking result in the end. And if you let this run long enough, you do actually end up getting something that's very, very close to the reference. You can also see this in the loss on the right. So now that we have something that works, let me kind of summarize what you saw in the last 20 minutes. So we started with a problem that's actually kind of tricky to solve, right? We want to generate texture bitmaps that are lower resolution but don't change the look of the material. And the simple approach of just downsampling the textures didn't work very well. Now, what I haven't mentioned is that there are actually dedicated techniques that can do better, like the work of Michael Toksvig, but they actually need quite a bit of work to implement, and they only work for a very specific class of material. And if the material that you have doesn't fit into this mold, well, then you'll have to invent something new. You'll have to invent a new bespoke downsampling technique that works for this new material you came up with. And all of this sounds like a lot of work. It's a lot of effort, and it's effort that you need to keep doing as you add more materials to the system. The alternative solution that you saw Chris and I explain was to first just find a way to measure the error between what you would like to happen and what actually happens, and then you just make that error smaller by adjusting the current textures that you have in an optimization loop. The most important thing here is that the bulk of the code that you write for this is just the code for doing inference. the code that does the rendering of the material in exactly the same way as you would when you actually go to use it, say in your game. And you can go and change that code, right? You can drop in a different material shader with textures that mean something entirely different. Heck, it might not even have a normal map. And you don't really have to change anything else. You don't have to come up with a bespoke new technique for mip-mapping this specific new material shader that you dropped. You just let the compiler generate a new backwards derivative, and you're off to the races. And this is really what's exciting about neural shading, right? Even though there were no neural networks here, this is already really quite useful. Problems that, were kind of tricky or might be really difficult in the classical approach can suddenly become very easy when your shaders become trainable, because you don't have to come up with an algorithm that generates the solution directly, and that algorithm might not even exist. But instead, you just iteratively improve your solution by running your inference code a bunch of times. And using tools like Slang that run in the graphics pipeline and have auto-differentiation, there's fairly little extra code involved that isn't your inference code, the code that you actually care about that produces the pixels in the end.